privilege to be here this morning. And thank you for such a warm introduction. It was too long. Anyway, we will see what I can do in 1.5 hours of time. And we will talk of robotics. We will talk of artificial intelligence, machine learning, and how it is driving Industry 4.0. Without much delay, let me start my formal talk. For that, I will stop my video to save some bandwidth and try to get the slides. So let me know if you can and see the slides on your screen, and that would be brilliant. I hope the slides are visible.
Yes, sir.
Sir, it is visible, sir.
Okay, thank you very much. So today we talk of a lot of things, robotics, and then AI and machine learning, and how it is driving Industry 4.0. So that driving word is very important for us. I would first give you an introduction of the history that has somehow motivated a group of people dreaming beyond their years and trying to really get to the very core of what we call AI today. It all started, if you want, and if we forget the mythological characters that people have dreamt of, as of history, it did start with the dreams of Aristotle. So Aristotle, way back in 300 BC, he had dreamt of a society where shuttles in a loom could fly on its own. There would be mechanical musicians playing the lyre. And then he says that if that happens, then there would be no need of servants or masters of slaves. So by a way, he justifies slavery by saying that such things are beyond our dreams now. But then the very idea that people could think of having automated machines that could weave cloth, automated machines that could really play music, was something that had set the ball rolling for the dreams to take shape decades later. It was Thomas Hobbes who, for the first time in his book Leviathan, justifies our ability to have an artificial life. So he says that life is a motion of limbs. And therefore, why is it not possible to have automata that could create what we today call artificial life? Thomas Hobbes, in his book Leviathan, puts the very idea of artificial life for the first time. And therefore, science historian George Dyson.
Hazarika sir, sorry to interrupt you.
Yes.
But your sound is very low, sir.
Okay, sound is very low. So let me see if I can do something. Is it improved now? No?
No, sir, no.
Oh. Why is the sound low? I have no idea, no clue. Can you hear me now? Not even now?
Some participants are not able to listen, sir.
Okay, so I will do one thing. I will go out and join again and see if it
Sir,
improves.
sir. And you check your speaker also, sir.
Yeah, I will do that. So can you hear me now better?
Now it is better, sir.
Okay, okay. Uh, Let me see if this remains. Otherwise, I have to go back and join. Our institute network is very poor nowadays. Anyway, so it was George Dyson who really had looked at Thomas Hobbes justifying artificial life in his book Leviathan and calls him the patriarch of artificial intelligence. Later, we'll see that artificial intelligence term itself was introduced by McCarthy. But George Dyson and considers Thomas Hobbes to be the patriarch of AI, for he was the first to think of artificial life. Dr. Tosif, can you hear me now? Hello?
Yes, sir, you are audible.
Clear, sir. It's clear,
Okay,
sir.
thank you very much. Thank you. So let's quickly look at the history of artificial intelligence as it grew out of the history of robotics. And let's try to pinpoint some important moments in the history of robotics that had made it possible for it to see the day today. So it was in 1948 that a neurologist, Dr. Gray Walter, wanted to model the brain functions. And in order to model the brain functions, he built two small mobile robots. These robots were called tortoises and were a marvel of the day because if you look at the date, 1948, we had basic analog circuits, vacuum tubes, and with just touch and light sensors, he could model these tortoises called Elmer and Elsie, and they could do decision making in a way that if somehow their batteries ran out, they could go to the nearest charging station. Now, this was a huge jump in the dream that Aristotle had seen about an automated loom. And about artificial life, to a point where people had really created small machines that could have some form of decision making. I, however, feel that this was not a very exciting moment and in the history, and therefore just call it significant moment number 2 in the history of robotics. Moment number 1 that had changed the face of robotics was yet to come. And it happened around 1962. So what is that moment in the history of robotics? Let's try to trace that point. It was in 1956 that Joseph Engelberger, who was an aerospace engineer, he met George Deville, an entrepreneur. And Engelberger told Deville about a patent that he was trying to file. And it was about a manipulator. A manipulator as a series of links and joints that could the control from the last link, and the end effector link could pick and place things. George Devil immediately saw what that Engelberger could do, and together they formed the first company to work on robots or make robots and call it Unimation Inc. But it was not until 1962 when General Motors became the first company to install a Unimate robot to extract hot parts from a die casting machine. And this is the most significant moment in the history of robotics, where for the first time, a automated machine was used in a manufacturing pipeline. It was not until 70s that people really considered putting some form of decision making into these robots. And it was only in late 60s and early 70s that researchers in the Stanford Research Institute began work on what they call an intelligent robot. Now, this mobile platform could reason on its own. It had camera, laser rangefinder, and radio link frequency to really do some form of decision making to move from one point to another. Because computation was very poor at that point of time, the decision making was very long. And when it moved, the robot really shook vigorously, and therefore they call it shaky. But then shaky was a turning point in the history of robotics. For this was the first robot that had artificial intelligence built into it. Whatever artificial intelligence means, I have not even defined that. But then, for just a layman's understanding, it had some form of decision making based on sensing the environment. And this is perhaps a very important moment in the history of robotics. So what I have done in the last 10 minutes or so is trace for you the more than 100 years of robotic history. It was only in 1920s when Karl Kapek and his brother Joseph introduced the term robot to describe mechanical man that took commands from its inventor, are in a science fiction and called Rosam's Universal Robots. So in 100 years of history that I traced in just 3 important moments, the most significant of them is, of course, the point in history when robots were introduced in the industry, 1962. The first robot to become a part of General Motors die casting system. So that brings us to the question of what is a robot? According to the Robotics Institute of America, a robot is something which is reprogrammable, multifunctional. So it is reprogrammable and multifunctional, and it is designed for performance of a variety of tasks. So until you can reprogram or it is designed to be multifunctional, you cannot talk of robots. other hand, the Japanese Industrial Robot Association and has a very inclusive classification of robot. For them, robots could be also manual or sequential or programmable, any manipulator that you can see. So the JCB machines that you see working on the roadside, lifting in huge amount of earth from one place to another, are working through hydraulic systems and manually controlled by a person sitting at the console, is a robot according to JIRA classification. Numerically controlled machines, the CNCs, NCs that we talk of, are robots according to JIRA. Any system that has sensory feedback, any system that can adapt its operation based on feedback received, and any smart machine system, according to the Japanese Industrial Robot Association, is a robot. And finally, if you have mechatronic systems which take sensory readings and change their behavior, that's intelligent mechatronic systems, are robots according to JIRA classification. So to take a breather, the Robotics Institute of America defines robot to be multifunctional and reprogrammable, whereas the Japanese Industrial Robot Association considers manipulators, numerical control machines, sensates, adaptive systems, smart systems, and intelligent mechatronic systems to be robots. So that is what we need to realign our thinking. The moment you talk of robots, you think of either a sophisticated manipulator or you think of a humanoid. But very simple systems like the fan switching system as you enter the room and go out is an intelligent mechatronic system and is classified to be a robot by the Japanese Industrial Robot Association. Under this is definition and the changing world, the ultimate goal is to create machines that would have some amount of perception. And when I say some, I mean to the levels of human perception, would be intelligent and efficient, and to really behave or exhibit behavior that we could classify to be intelligent. So the emerging technologies in robotics research is about getting physical machines which have almost human levels of perception and as intelligent and efficient as the human interfaces. And that is where the concept of AI comes into robotics. Artificial intelligence is what is demonstrated if I'm talking of accomplishing a task and that requires the ability to learn. So any task that requires the ability to learn, if that can be done by a machine, then I say AI is demonstrated. So look at the link that is very, very important for this is understanding. Robots as we see today, anything that exhibits human level perception skills, if possible, and some form of intelligent and decision making that we exhibit, it are classified as robots. Now, when I say intelligent, what I mean is any task that requires the ability to learn, earn, and when I say learn, I mean learn, reason, and solve. And if that can be done by a machine, then we say that AI is the machine is an artificial intelligent machine. or AI is demonstrated. Now, robotics gives the demand for intelligence. Intelligence gives the demand for learning. So anything that has the ability to learn. And therein lies the genesis for machine learning. So the link is from robotics to AI to ML. Okay? But before we move on to ML, let's look at a little bit on what actually is supposed to be artificial intelligence. It was in 1950s, Alan Turing wrote a very interesting paper called Computing Machinery and Intelligence, published in the journal called Mind. And he speculated that it must be possible to create machines with true intelligence. But then, what is intelligence? In order to define that, he devised his famous Turing test. The Turing test is possibly the first and the serious proposal in the philosophy of artificial intelligence. What is the Turing test? Before we go into that, let's look at what he wanted to call an intelligent behavior. So in his paper, Computing Machinery and Intelligence, Alan Turing starts the paper by saying, I propose to consider the question, can machines think? And go on to define what thinking means. And if you exhibit thinking, you are supposed to be intelligent. So the Turing test was about a blind wall separating a human interacting with either a machine or a human. And if the man on the other side of the wall cannot decide if the answers are coming from the man or the machine from the other side of the wall, then the machine would have passed the Turing test. No machine as of yet has cleared the unrestricted Turing test. It was in 1956 that McCarthy organized a conference that's called the Dartmouth Summer Research Project on Artificial Intelligence and used the term AI for the first term. He is credited with coining the term AI. The Dartmouth conference was path-breaking in the sense that some 2-month, 10-man studied this idea of creating artificial intelligence. And they came up with a conjecture. The conjecture being that every aspect of learning or any other feature of intelligence can in principle be precisely described so that a machine can be made to simulate it, or what we call written in form of an algorithm. So they said that every aspect of learning or every feature of intelligence can be expressed in terms of algorithms. And this laid the foundation for what we today call the symbolic AI, artificial intelligence in terms of manipulation of symbols. One thing that's very clear in the years AI has been pursued is the fact that any form of intelligence requires knowledge. And that knowledge has to be acquired. So machines need the ability to explore the world and acquire the requisite knowledge. This is where learning comes in, because all knowledge that is acquired by a machine is only through a process of learning. So robotics the very fact that I would have robots which could make decisions on its own pushed me towards artificial intelligence. Artificial intelligence and or intelligence of any form requires knowledge, and that pushed machines to have the ability to explore the world to acquire the requisite knowledge. And this is knowledge acquisition is through a process of learning, giving birth to what we today call machine learning. So in terms of a computer program, if I want to decide machine learning to be, then a computer program is said to learn from experience E with respect to some class of task T. If given an increasing E, its performance P increases. So as you give new experience to the program, your experience could be anything and everything. But for a very restricted definition, you could think of new data given to the program. So as you give new experience to the program, the performance of the program improves. And if it improves, then I say that it has learned. And such a program is said to be a machine learning program. I repeat it for the sake of clarity. So if I am given a program, and if I can give experiences to the program, as the program gains more experience, its performance improves. And if it improves, then the program is said to learn. If you look at the early history of machine learning, it was Arthur Samuel working for IBM who first developed the very idea that you could have programs that could learn on its own as you give it new experience. So Arthur Samuel is the pioneer in the field of computer gaming and artificial intelligence, and is credited with coining the term machine learning. In his path-breaking paper in 1959 called Some Studies in Machine Learning Using the Game of Checkers, Arthur Samuel writes some checker playing programs that could play checkers as with a human. And as it played more checkers, it gained experience and learned to play better. IBM shares were going down, and Samuel went live on television playing checkers against an IBM P700 machine, and the fortunes of IBM turned overnight. So that's not the main story. The main story here is about Arthur in 1959 giving birth to the area of machine learning, wherein he wrote the checker playing program. And the checker playing program is perhaps the world's first self-learning program, and was a very early demonstration of the fundamental concept of artificial intelligence being achieved through machine learning. So in terms of the definition of machine learning by Tom Mitchell that I gave a little while ago, if you look at the checker playing program, then T is the task of playing checkers, P is the percentage of games won against the opponents, and E is the playing practice games against itself. And as you played against the program learned more rules, more ideas, and finally improved its performance speed. In his paper, Samuel says that the checker playing program could learn and play checkers better than the ones who had programmed it. And this was a huge step in the path towards artificial intelligence. So machine learning, what is machine learning? It is about building a model that is a good and useful approximation to the experiences given to the program. And the model is defined by some parameters where it is about learning to optimize the parameters of the model. So let's try to compare traditional programming vis-a-vis machine learning. So almost all of you must be aware of traditional programming. You have data given to you, you have a program, and you expect an output. That's traditional programming. But machine learning is when you have data, you know what this data is telling you. That's the output. You know the data is telling you about something, so you know what it is telling you. What you want is a model to describe this relationship between the data and the output. And that model is referred to as a program. So you want a program that could explain the data given the output. And then what you can, of course, do is take this program, plug it into your traditional idea to get new output, take that output and plug it into your machine learning to get a better approximation. So this can go intertwined until you are very satisfied with the way the data is explaining the output. That is, you are satisfied with the model that you have arrived at. Now, this very idea of machine learning is what we follow when we are looking at data analysis or we are looking at analytical model building. So machine learning somehow focuses on the cognitive learning capabilities and is some form of problem solving, where we want to look at the input data and describe them using a model that best describes the output that we have. So having introduced that and having a FDP on artificial neural network as part of your FDP topic, so I thought it would be appropriate for us to understand and the link between these topics that we are talking of. So if you look at the taxonomy of artificial intelligence is a superset. And in that superset, you have machine learning, which is about the idea of getting to describe the data in terms of a given model. Now, the idea to really get to the cognitive model of the brain or the brain-inspired architectures lead to a completely different idea of artificial intelligence. Remember, I told you McCarthy introduced the term artificial intelligence in 1956. And he said that we could have any intelligent behavior or any feature of intelligence and in terms of an algorithm, in terms of a sequence that could be computed by a machine. So in terms of an algorithm. So he gave rise to a principle of AI, which we call and paradigm of AI, which we call symbolic AI. That is, any intelligent behavior is symbol manipulation. Like in school, you were told to exhibit your intelligence in arithmetic. So you were asked to subtract 5 mangoes from 7 mangoes. So how did you do it? You replace the mangoes with symbols, and the symbols could be your fingers. So you took 7 fingers, and then you took 5 fingers away, and then you said you are left with 2. So that symbol manipulation was some form of capturing the idea of intelligence.
So there are interlinked biofactor K, which is called as a efficient.
So that is the idea of symbolic AI. On the other hand, and people wanted to get the human intelligent behavior by copying the neural connections of the brain. So this idea, which copies the neural connections of the brain or creates neurons and a network of neurons, is the idea of neural nets, okay? Which is some form of brain-inspired artificial intelligence. Very close to this idea of neural networks is the idea of spiking neural networks, which are, of course, artificial neural networks, but they closely mimic the natural neurons or neural networks, because in addition to the neuronal structure, neuronal structure and the synaptic state that the ANN, and which I am sure or one of the lectures would cover, emulates, the spiking neural network incorporates the concept of time into their operating model, making the ANNs even more exciting. And then finally, we have this idea where ANN networks use deep architectures, that is, not 1 or 2 layers, but huge layers of artificial neural networks, giving rise to this idea called deep learning. So as you see, AI is the superset. Inside it, we have machine learning. And then in machine learning, the brain-inspired machine learning or AI system has spiking neural networks and artificial neural networks, 2 ideas. Artificial neural networks, when you have deep architectures or huge number of layers of them, or hierarchical learning approaches in them, leads to what we call deep learning, a subset of machine learning. So that's the taxonomy of artificial intelligence. Now, given this understanding, and given the understanding that AI and ML has pushed its boundary, starting with the vision of getting really intelligent and machines. So robotics is behind this push. If you see the timeline, you have AI and ML, and then in 80s machine learning came, and in 2010s we have deep learning. So we should be able to get to the very idea of where we are heading as a society. So according to a very interesting book published by Timothy Chow, a professor in Stanford, called Precision: Principles, Practice, and Solutions. This is about precision engineering. He says that the engineering of the future would be just by the right amount, at the right time, at the right place, nothing more, nothing less. So according to him, the future machines, even if it would be an assembly of parts, gears, and electronics, the machines would be integrated collections of sensors and actuators connected by software. Like here, I have Elon Musk's famous car, are the Model S, which according to Elon Musk himself is not a car, but a sophisticated computer on wheels, because it has so many sensors around working for it. Forward-looking camera, then you have small radar, you have 12 ultrasonic sensors, you have information from camera supplemented by GPS and whatnot. So that is what the future is, where we would have sensing in huge amount, more than even the human perception levels. That sensed information would be able to be made sense of by the principle of machine learning. The sensed information would be our experience E, which would improve our performance P. So some form of machine learning would be always working behind such machines. And this would give rise to what we call precision engineering, the ability to have the right amount at the right time at just the right place. So given that, the revolution that's happening in manufacturing or in the industrial world is very, very important. So that tracing that is what I would do in the remainder 40 minutes or so that you can understand why we are talking of Industry 4.0 today. What makes it so important as mechanical engineers? What makes it so important for us is the very fact that starting with Aristotle's dream, we have come a long way from science fiction to the robots of today, where sensing, planning, and acting has been such intricately managed that we are able to have what we call intelligent systems. So if you look at the evolution of industry, mechanical production machines powered by water and steam was possibly the first industrial revolution. Then there was electrical energy, mass production lines powered by electrical energy created the second industrial revolution. We had the third industrial revolution where use of electronics and information technology further made progression in autonomous production. And today we have huge connected networks giving rise to what we call cyber physical systems. So the very basic of industrial revolution that is happening today, called Industry 4.0, is based on cyber physical systems. So Industry 1.0, water and steam, somewhere around 1784. Industry 2.0, electrical energy, making ways into production lines, 1870. IT and electronics, making a headway, late 60s. Robotics, AI, big data coming together. And that, for understanding this, 45 minutes I've been talking to you about how robotics has progressed over the years to give rise to AI, and AI has pushed its boundary to give rise to ML. That is happening now, and that's Industry 4.0. So Industry 4.0 is the current trend of automation and data that's exchanged in manufacturing technology, including what we call cyber physical systems, Internet of Things, and artificial intelligence. Now, if you look at this push, if you look at this idea, okay, then you would see that with increasing data volume, variety, and complexity, and with increase in the complexity of our inventions, where we started way back with the handicraft age, moved on to machine age, then we had information age, and today we have big data connected age. Okay, the fusion of big data and communication. So all of this has pushed data into manufacturing in a huge way, giving rise to Industry 4.0, which is about having smart sensors, smart controls, smart connectivity, leading to smart factories. So these are the four building blocks of Industry 4.0. Smart sensors, So sensing capabilities, remember I told you before, sensing capabilities that are beyond the human perception, controls, connectivity, and smart factories. They together build or create the idea of Industry 4.0. Industry 4.0 is about digitization of the operation and integration. So it's digitization of both the vertical and horizontal chains. It's about digitization of product and service offerings from the industry. And it's about digital business models and customer access. So all of these need to help happen together. And at the core of it lies data and analytics. Okay? So we may be talking of mobile devices, we may be talking of Internet of Things platforms, location detecting technologies, advanced human machine interfaces, 3D printing, smart sensors, big data analytics, okay, augmented reality, cloud computing. But all of these are periphery. At the very core lies data and analytics as a core capability of bringing together digitization and integration. And this is happening because of our capabilities in what we call today the IoT or the Internet of Things elements. So, what is IoT or Internet of Things elements? Let's take a minute to understand that before we move further. So, the Internet of Things, if you look at, is about identifying every component involved in manufacturing. Thereafter, having capabilities to sense its environment. So identification, sensing, thereafter communicating the sense data to some place where you could compute or process and then provide the service that you're looking for. And finally make meaning out of what has happened. So these 6 elements constitute what we call the Internet of Things: identification, sensing, communication, computation, services, and semantics. Identification is about having identifiers for each and every element that's working. The robot, the sensor, the computer, everything needs to be identified. Each of them needs to have a name, and unique name for that matter. Each needs to have the capability to sense its environment and tell what is happening or how it is acting. The sense data needs to be communicated over a communication network to a place where it could be processed or some computational facility. And then that facility needs to be able to advance some service through disconnected components. Once that services are offered, in retrospective, they should make meaning out of what has happened just now. And that meaning is nothing but learning in the process of really operating as it goes from identification to sensing to communicating to computing and providing the service required. Identification is about getting the name correct. So it's critical to differentiate between object IDs and their addresses. So every object needs to be connected, but they must be identified. Sensing is about gathering data from related objects using some sensors as actuators or wearable sensing devices. And then communication, I highlighted before, is about getting the things communicated to a place where it could be computed. Okay? And processing units or the computational units could be just hardware platforms there itself on the shop floor, or it could be something on the cloud. And then the ultimate goal is to reach the level of ubiquitous service. That is provide some information aggregation and collaborative aware services to the system. And finally, you need to really make meaning out of what you have just now done, or you need to have the ability to extract knowledge. And extract knowledge is nothing but creating intelligence. So in the whole process, you create intelligent systems. You discover and use resources and modeling information. So digitization and integration over the IoT elements lies at the very crux of creating Industry 4.0. But you should understand that this has not happened overnight. This is what happened by its natural process as I have moved from industry a 1.0 to 2.0 to 3.0 to 4.0, starting with steam to electricity to information technology to this cyber physical system, creating systems that are completely networked together, okay, integrated, and not only digitized but integrated. So core design principles lie at the very crux of Industry 4.0. You need to have interconnection, you need to have information transparency, decentralized decision, and technical assistance. Things that are happening simultaneously on the other side of this wall all are more interesting ideas, such as cooperative robots. So cooperative robots, if you allow me, are robots that no longer remain confined into an industrial cell. So when robots were introduced for the first time in the industry, there was the question of safety of the industrial worker. So the robot was confined to a shell, which was usually a wired mesh enclosure within which the robot was supposed to operate. And to start with, the robot was seen to replace the human worker. But as we made progress in robotics, people realized that robots could best be used to augment the human capabilities rather than replacing them. So robots today are seen to be augmenting the human capabilities. And as they augment human capabilities, the very idea of keeping them confined to a cell and wired mesh enclosure is breaking away, and robots work in close proximity to human beings. Further, today, robots are made to work in cooperation to one another. So you could see a team of robots working together rather than single robot being planned to work out a particular function. And that's given rise to the idea of cooperative robots, robots working in cooperation with one another, and robotics, cooperative robots working in cooperation with the human, okay, to augment his capabilities. So this is a huge step in the way towards Industry 4.0, or the industrialization of the shop floor. So collaborative robots is what is more exciting than just cooperative. So a little while ago, I was talking to you about a cooperative robot that cooperates with the human being, and you don't need to put it within an industrial wired mesh. A collaborative robot, in contrast, works in direct cooperation with the human. Okay? And this is about not only looking at the physical capabilities of the human, but also the cognitive capability. So if I'm talking of a collaborative robot, I need to have ways and means of understanding the physical as well as the cognitive capabilities of the human worker working in close cooperation with that robot, so that the robot can really provide the type of cooperation required based on the capabilities of the user. So many of these collaborative robots are used in pharmaceutical industry, in robotic rehabilitation, and in clinical practice. In robotic neurorehabilitation, such collaborative robots have come a big way, because if somebody is given some form of physiotherapy, doctors want that the amount of physiotherapy should be as as appropriate as required, nothing more, nothing less. If you give more, then the person loses whatever he had the abilities. So for what is called retention of residual skills, you do not want and the robotic neurorehabilitation robot to give assistance more than required. And at that point, we need to have a collaborative robot, which is a robot that can make or access or really make a judgment of the cognitive as well as the physical capabilities of the patient, and then provide assistance as needed for retention of residual skills. So collaborative robots work in direct cooperation of humans. This could be inside a defined workspace, and then it could be both industrial and non-industrial environments. As I have highlighted, it could be in clinical practice, in pharmaceuticals, apart from just hardware manufacturing industries. And they really is about augmenting workplace capabilities. This is something that we need to really understand as we move forward in taking robotics towards our vision of creating in Industry 4.0. Robots are not about replacing the human worker. It is about augmenting the workplace capabilities of the worker. So it will bring in efficiency, it will bring in repeatability, it will bring in power and precision. And one should see robots being used in that context rather than in the context of using a robot to replace the human, as was done in 1962. In 1962, when I was telling you about the first use of robot in the industry, a Unimation Inc. that made the robot were unable to sell these robots called Unimates until they went to General Motors and argued that die casting machines, workers' health and safety was a threat because of working in the die casting machine, pulling out really hot dies from the die casting machine, and a robot could be used to replace the human. But that is no longer true today. Today, robots augment the workplace capabilities to improve performance in terms of precision, in terms of power, okay? Rather than replacing the human worker, as done by Unimation Inc. with its Unimate robot in 1962. So at the very crux of this idea of robotics driving AI, AI bringing in machine learning, and the world changing in terms of creating a connected world leading to Industry 4.0, lies this 6 path-breaking transformations transformative technologies is or digital transformation. One of them, the machine learning, we have really looked at very closely, if you want to say it that way. I have not defined for you the different types of machine learning because I thought it's not important for our discussion today. But just for completeness sake, let me do it here. Machine learning can be thought of in three distinct paradigms or modes. Supervised learning, when and I do give experiences or I give data and then give the output vector together, saying this is how the output is expected to be. So then the machine learns. That's supervised. So it's like your kindergarten school teacher teaching you that apples are red and you have red roses, as by showing you a red rose and by showing you an apple and stuff like that. So there is a data and there is a output vector given to you, and if you can have a model out of that, then that's called supervised learning. Unsupervised learning, on the other hand, it's about giving you the data and not telling you anything about the output vector. You have to make sense of the data yourself. So things like putting data in classes by looking at the neighborhood or what we call clusters is unsupervised learning. Then we have a very interesting idea of learning called reinforcement learning, which is gaining importance today rather than supervised and unsupervised, is the idea that as you do the stuff, you get a return from the environment. You want to do it the way to maximize the reward. So, like, take the example of a monkey being taught to ride a bicycle by the Madari. So you have this monkey riding the bicycle, and if the monkey rides the bicycle right, you give it a banana. So the monkey is riding the bicycle not to learn, but to get the banana, to ensure that the reward is maximum. Okay? And in the process, he have learned how to ride the bicycle. Or his ideas of keeping balance, paddling is reinforced. So that's reinforcement learning. Okay, and these three models have made a huge digital transformation and in our path towards creating Industry 4.0. The next technology is about additive or hybrid manufacturing, in where it's not about removal of material to create objects, but it's about adding material to create objects. So it's additive manufacturing, what we in common parlance call 3D printing. But additive manufacturing is more than 3D printing, as I will see in a little while. Then there is the idea of knowledge automation. So it's about knowledge is not only being created. Okay, so if you look at this is idea that the sensors create a lot of data. As you process this data, you create information. And as you try to understand this information, you create knowledge. And this process is automated. Okay? So let's look at this way. I have a building where all of you are sitting, and you know there are 7 windows and 2 doors in the building. That's data for you. And the information is the windows lead to a balcony, and the door leads to the corridor through which you can go out. So you have processed this data to create information. Knowledge is when you can process this information. Like, given the doors getting blocked because of a fire, you can use the windows to go out and land on the balcony. So that's knowledge, because you could process them, given new information to you, that the doors are blocked because of a fire. So this process of deriving from data some information and from information some knowledge is this automated process has given a huge impetus to our idea of cyber physical systems leading to Industry 4.0. And then we have this idea about big data and analyzing it, and digital twins and advanced robotics, which I will talk of in a short while from now. So cyber physical systems, what is a cyber physical system? Let's look at that definition first. So whenever we are talking of collaborative computational units that are controlling some physical entities, we say we have created a cyber physical system. So what do we mean by collaborative computational units? Collaborative computational units are the units of control, units of communication, and units of computation. So if we have a control system which can communicate and then compute and give me what to control back, that creates a cyber physical system. The control system could have sensors and actuators as well, and the communication system can provide information, and from the sensors to the computation can make sense of it and give you back what to control. So information and is the binding factor between these elements. So if you have collaborating computational units, it's controlling some physical system, and these computational units are bind together by information exchange, then we create what are called cyber physical systems. Okay, and the cyber physical systems lie at the base of manufacturing automation. So enabling technologies that allow us to realize cyber physical systems in manufacturing involve, in terms of connection, all these data acquisition and feature extraction systems that we have allows data technology. Machine learning allows some analytical technology to us, and then we have prognostics and visualization, finally control optimization and design feedback. So these enabling technologies allow us to create cyber physical systems in manufacturing, leading to very interesting what we today refer to as data-driven smart manufacturing. So what is data-driven smart manufacturing? One should understand is that this lies at the very core of Industry 4.0, but created using the very concept of a cyber physical system, where you have control, or you have communication, you have computation, all brought in together, and this could be a bringing together of all your or processes or workflows like customer relationship management, manufacturing execution, enterprise resource planning, product life cycle management, everything put together. So you have material input coming into your system. You have all of these cyber physical system created where information exchange can happen over data, which could be transmitted to make some decision. The decision support can be fed back to the system. And if you have some operational control issues coming in, that could be analyzed again and using in some real-time running state analysis is to give you the problem solving leading to the manufacturing module, and all of these integrated leading to what we call data-driven smart manufacturing. Okay, this lies at the very core of Industry 4.0. The concept is also extended and beyond that to a term called agile manufacturing, where it is about an organization that has created the processes, tools, and training to respond quickly to customer needs and market changes. As an agile manufacturing is mostly about manufacturing based on customer needs. So there are four core values in agile manufacturing in that pushes it as a model for industry 4.0. You have real flexibility in the terms that the operation can take place. You have bottom up processes as through which you can reorganize the pipeline and allows you rapid integration. And then, of course, robotics comes in to have augmented workers, making it all possible for you to really make adjustments and change things very fast as the requirements arises. Many emerging technologies like nano electromechanical systems, which is about integration of mechanical elements, sensors, actuators, electronics on a common silicon substrate, it is a contributing technology or an emerging technology for Industry 4.0. NEMS, as we call it for short, these are about micro machining processes and enabling technology which allows development of smart products. And here I mean smart by one that allows sensing and actuation and control at the same time. One of the most emerging technologies, if you have seen, I have listed it there before, or in the 6 technologies that I have named, is the technology of digital twin, which I said I will talk of later. So digital twins are actually digital representations of real world objects. Now, one needs to understand that digital twins are not just the CAD or finite element analysis model or just the physics-based models or statistical models. They are CAD models, finite element analysis model, physics model, statistical model, machine learning, AI model, all into one. So it's like the digital avatar of the main machine. What do we do with that? We do not operate the machine. We operate the digital avatar, get its operational history, get its failure, get its maintenance history, therefore. And we then aggregate the fleet data into the enterprise system to really talk of the machine on the shop floor. So the machine on the shop floor that's operating has everything happening for it for just the right moment at the right time by the right quantity. Okay? And that is made possible by creating digital twin model. Now, you would be very pleased to know that the digital twin model, one of the world leaders, is an Indian company, a Tata company called Voltas. So Voltas is one of the first of the companies to implement digital twin technology for all their industrial chillers. So the chillers operating in the industries all over the world are not to be maintained by site engineers any longer. All of their operational maintenance aggregate fleet data is available at the Pune office. And then they have integrated it to the enterprise systems of each of the chiller companies, each of the chiller are holding companies, and they operate it that way rather than having a service engineer in place looking at things, failure or maintenance. Now, you should not confuse this for predictive maintenance either. It's not predicting failure. It's actually operating the avatar and getting everything that can happen to this based on the digital twin. And whatever can happen, they are taking care of when it needs to be taken care of. And that is the emerging technology that's making Industry 4.0 so exciting. One of the last technologies or the last things in the Industry 4.0 scenario, if you remember, I started with was the smart factories. So the smart factory is what we would have in the future, or it would have integrated supply lines with stock optimization. So there would be just in time inventory, additive manufacturing, collaborative manufacturing with instant analytics for agile systems, complex design customized with augmented real-time machine communication and with robots, leading to smart logistics. And basically, because of the communication network, because of the cloud computing facility, we would be really creating what we call on-demand manufacturing, rather than manufacturing things and stocking them up and sending them out. So this is what the future would hold in terms of Industry 4.0. Finally, where is the future that we are talking of? Where are we going? We have looked at a lot of digital mapping and visualization. We have looked at predictive proactive maintenance, reduction in production, logistic quality management cost, reduce complexity cost, real-time coordination of value chains, flexible customized mass production. So these 6 elements would drive future industries. If you are not into this, you would be left out, and you would be left behind in the industrial revolution happening now. It's very important that people readjust their industrial shop floor, readjust the way they look at manufacturing to really bring in these 6 elements so as not to be left behind in this industrial revolution. Then there are other trends that's coming very fast, and for that we need to brace up soon. The one that's coming in additive manufacturing is the 4D printing technology. So 3D printing was about additive manufacturing, getting to a 3-dimensional object. 4D brings in the possibility of self-assembly over the 4th dimension, which is time. So self-assembly, so you print objects, but these printed objects then reshape themselves or self-assemble over time, giving rise to what we call the 4D printing technology. Another very interesting technology coming very fast in this 4th industrial revolution is the idea of self-assembly or living materials. So the healthcare market could use technology for tissue engineering or what are called self-assembling biomaterials. Okay, they are self-healing materials. They take shape on their own. After 3D printing, they need not go through this process of assembly. So they can take the shape that they were really working with. And if it breaks in one point or other, it could heal and make bridges and make amends to itself. So such technology would be in the near future used for building roads or bridges, which would be self-healing. These are futures. Okay, the final 2, the 4D material, the 4D printing, the living material, the self-assembling ones are the future. So I have taken your time today morning to give you some introduction to the history of robotics, starting with the very idea that Aristotle had with very interesting ideas by not only in science fiction, but real world, creating certain moments in the history of robotics, leading to the first industrial robot being introduced in 1962, and then the first intelligent robot being made in Stanford Research Institute around 1970s. That pushing forward our agenda of artificial intelligence, making knowledge part of it, knowledge acquisition, and making exploration a theme, leading to machine learning pushing boundaries to create systems which are not only based on symbol manipulation, but trying to copy the human brain and create artificial neural networks. And then we have seen simultaneous to this progress in robotics, AI, and ML, the other progress is leading from steam, electric power to information technology and cyber physical systems, pushing the idea of Industry 4.0, and how the confluence of robotics, AI, and ML and these idea of cyber physical systems coming together is creating the smart factories of the future. So this is where we are moving. And as artificial intelligence seems to emerge from science fiction to becoming the frontier of world-changing technologies, we as engineers have a very important role to play for systematic development, of components, systematic development and implementation of AI modules to see its real impact in the next generation of industrial systems, which we call the Industry 4.0. Thank you very much for your kind and patient hearing. If you have any questions, I would be free to take them now.
Thank you very much, Professor Hazarika, sir. It is a very nice talk. As I've already heard your so many presentation online, and I am a big fan of you, sir.
Thank you very much.
So it is a time for query session. The participants can unmute and ask their queries to Professor Hazarika, sir.
Good morning, sir.
Good morning.
Sir, I want to ask a question. Means, can you explain a little bit more about reinforcement learning? Like, sir, this is the concept from psychology, and in reinforcement learning, like the example which you have given us, the monkey is learning, when actually it is not learning. Just to get the banana, means learning is unconscious. So, sir, how software agent is doing the same?
Very, very good question. How a software agent is doing the same. Okay. So in this, we have to look at three things. Okay. As you kindly and rightly pointed out, we have a software agent. So there is an agent program and there is an environment program. Okay. There is the rest of the agent. Anything which is not the agent is the environment. So we have the environment, we have the agent.
Yes, sir.
Now comes
Yes,
in the idea to teach him reinforcement. So the agent, whenever it works on the environment, gets back a return. That return is called a reward. So it's in two places. The agent operates and we have an environment. The agent operates on the environment. The environment gives a return, which is called a reward. Okay? It's not about learning right now. So now the algorithm in the agent is that he will take only those actions which will maximize his return. So his idea is to maximize return. And in the environment, you create a system and such that when he gets the maximum return, his structure changes and he is given some information on the task. So he gets unconscious ideas of learning happens in the agent program. So the agent program tries to get a model of the world by not looking at the output and trying to create a model. He gets a model of the world by operating on the environment and the environment giving him a reward, and his only algorithm is to maximize reward. So he tries to maximize the reward. And here in the environment, you look for are different and optimization algorithms that will maximize reward for him. And as it maximizes reward for him, you would see that his his performance for the given task is also made to improve. Okay, this is how it happens.
Okay.
Okay, so
Thank you, sir.
to give you some idea, you have to have an agent program, and then you have to have a policy, and you have to have an environment. So the policy is to really get the agent, give you actions that will maximize the reward, and that you control the policy, and the agent and experience improves. Sorry, performance improves with experience. That is how it is done. Okay. Beyond that, if you want,
Thank you, sir.
beyond that, if you want, and you are from engineering or from psychology.
Sir, engineering.
Okay, so very good. So if you are from engineering, then reinforcement learning, the best place to read is a 10-hour course by David Silver. So search on the Google David Silver. A 10-hour course is there from University College London. 10-hour course by David Silver. It's free. So you learn reinforcement learning, where you will be surprised. The first video is about a helicopter, which he has taught how to fly using reinforcement learning. Yeah. So that,
Yes, sir.
you can look up that.
Thank you so much, sir. Thank you.
Thank you very much. Tofik, you are not unmuted, so you have to unmute.
Good morning, sir.
Good morning.
Sir, this is Sri Lakshmi. Sir, can you differentiate feedback from the reward? Both will give the information to the same program, no?
Very good, very good. So a reward is different from feedback. Feedback is when you have a control loop operating, and you get a sensor reading. Like let me tell you, you are supposed to make an omelette. Okay, you are a robot and you are supposed to make an omelette. So as you break the egg on your hand with a hammer, the whole of the egg spills on your hand. So your hand sensors can give you a feedback that it is egg all over your hand or palm. Okay, so that's a feedback. But as a policy for making an omelette, now I have to give you a number saying whether your breaking the egg was good or bad. And that I can give it by a reward saying this is minus 100, because now the program to make an omelette will never proceed further because you have spilled the egg. So feedback is when you have spilled the egg, your sensors give you the reading, but the reward that I give you in the action that you have taken is minus 100, saying I have no way I can proceed further. Okay, so when you are spilling the when you are breaking the egg, your idea would be to maximize the reward and therefore not spill it. But once you have spilled it, then the reward would be very negative, whereas the feedback would be, yes, there is a lot of egg on your palm. Okay, so that is the difference. Feedback is to get a control structure in place. A reward is to get a policy moving as you plan ahead to take an action and for our accomplishment of a task. Is that clear?
Thank you, sir.
Okay.
Sir, can you suggest us where we can start the reinforcement learning from the scratch?
So, are you an engineer, or all of you are engineers, right?
Yes, yes, sir. Engineers.
Okay, so if you have done a course in control theory, then reinforcement learning, half of it is already done. So reinforcement learning is based on what we had studied in control. So it's some form of a very advanced control structure. Okay. So I would say to start learning reinforcement learning, look up a very simple introduction to machine learning lecture from NPTEL or someplace. And then the best place to start reinforcement learning is, as I told a little while ago, is David Silver's course. So look out for David Silver's course on reinforcement learning. It's a very easy going course, not very difficult for starters.
Thank you, sir.
Else you can of course write email to me. I will give you more pointers.
So any other query of the participant, or should we stop the session?
Sir, one small 1 minute, sir. Sir, this
Any
is
other
very
query you may
informative.
discuss?
Yes, sir. It's very informative session, sir. It started from the scratch to the advanced level. It's very, very useful for all learners and all those things. We are very much understanded, and from the scratch to the till today, from the 1.0 to the 4.0. Sir, can you share your PPTs for our reference?
Yeah, PPT I will share later on. Don't worry about the PPT. All the PowerPoint
Okay, sir,
presentation we will share in the WhatsApp group.
Okay, sir. Thank you.
So at the end, I am very thankful to Professor Hazarika sir. There are very few words I have to say thanks to you. Sir has discussed very important aspects of artificial intelligence, machine learning. He has taken the discussion to the next level. And he also discussed about the intelligent robots, collaborative robotic system, cyber physical system. He also discussed about Industry 4.0, about the data-driven smart manufacturing concept, and about the digital transformation. So these are very important areas, or you can say the future areas of research in the field of artificial intelligence or machine learning. So once again, I am very thankful to you, Hazarika sir, for joining us, and I am blessed with your presentation, sir. Thank you very much for joining us.
Thank you very much, Dr. Tawfiq Siddiq, for having me here. Thanks. Namaste.
Thank you, sir.